Here we have a CRFS RFeye receiver, very capable piece of hardware, along with CRFS's open source Python client to access the equipment and perform a sweep in this case. And we have some data, so let's integrate.
One of the biggest issues in achieving accurate modeling is getting the noise figure right. If you get this wrong, if you just make a bad guess, you're building a house on some very shaky foundations. So the noise figure is down here in our templates in the output block, and it's this variable here, NF. It should be set carefully, and in the user interface it's set automatically based upon the bandwidth here. So a wider band signal carries more noise, and so you will get more noise with a larger bandwidth. I've deliberately picked a signal in a very busy piece of spectrum here, the 2.4 gigahertz ISM band, and it's quite ambitious what we're asking for here, which we'll find out shortly. The first test I'm going to do is a reference calculation just using our API client and a template, which is this one here. It's just telling us there's no spreadsheet because we're only doing one. That's fine. I've got a KMZ in a folder. I'm loading that into Google Earth to have a look, and I can see that my template is showing me a directional antenna shooting across some water here. So this is with our guessed noise floor. We just made a stab in the dark at this, and we're hoping it's right. Let's find out if it's right by connecting to the RFeye. So we connect to the RFeye with the new parameter, RFeye, and the address only. Everything else that the RFeye needs, such as frequency and bandwidth, is taken from the template. So now we get some more output. The noise has been measured. The noise is actually quite high. It's 92 dBm, minus 92. So I'm dragging this KMZ onto Google Earth, and I'm going to disable the old one, and wow, what a difference. So we've lost many decibels of coverage because of a higher noise floor. If I repeat this again, very close, 94. Right, 108 this time. And we can put that on. And then you can see that we're no longer leaving the airfield here. Now, if I wanted to see more of the spectrum, just to satisfy myself with what the spectrum looks like and understand why it's jumping up and down, if I put on verbose mode, not only do we get more output from our script, but we also now get a FFT. So we can get an FFT straight from RFeye, and that looked quite quiet. Minus 109 was measured, minus 109 was set in the template. So what I'm doing is I'm repeating the test, and what I'm looking for is that. So this is a Wi-Fi signal that's just popped up here towards the right hand side of the 2.4 gig spectrum, and that will bring up the noise floor. And let's have a look. The noise floor was measured at 103, and there it is, it's 103. And there's quite a large one here. So signals will bring up the noise floor and they will impact your modeling. With this API client, you can now connect to an RFeye and perform accurate modeling using measured noise floor values. The beauty of the RFeye is it's a network-based receiver, so you could conduct modeling with accurate values in a distant location without actually visiting there to take a noise floor measurement.